Okay, I'm going to do a second video in hydrostatics. Just noticed while looking over the first video that I made with the hydrostatics that I made one assumption that is not always valid. And that assumption was that we were dealing with a fluid that was incompressible, and that's not always the case. You could be dealing with methane, which is what we're going to do in this example. So let me just go ahead and pull up the problem that we're going to work through. And here it is. Scroll up a little bit. Okay, so you can go ahead and just pause video if you need, but this is the problem that we're going to work through. I'll go ahead and just kind of go over the highlights. So we have oil and gas well. We're given the height of oil and methane, and then we're given, we're told that the oil is incompressible, the entire system is isothermal, so the temperature is going to be constant throughout the entire system. And then we're told that the methane behaves ideally, so we're going to have to use that information. And then we're also given the specific gravity of the oil, and we're given the density of water, and then we're given the gauge pressure at the top of the gas well. So using this information, we're going to determine what the absolute pressure is at the interface between the methane and the oil, so that would be at point B. And then, so that's for part A, and then for part B, we're going to determine the pressure drop from point C to point B of oil. So let's go ahead and just get started on the problem here. Alright, so we were given all the units in imperial units, which I don't like working in, so I converted some of them to metric, and then I'll convert the rest to metric as we go along, and then once we calculate a final answer, we can go ahead and convert back to imperial units if need be. Alright, so let's go ahead and let me just go ahead and briefly discuss what kind of assumption I made during the last video, and that's the introduction to hydrostatics video, and why that's not really a valid assumption. So we derived an expression that said that differential pressure with respect to height is equal to negative rho g. And then I went on to separate and integrate, and then when I separated and integrated, I said this. So I said that pressure is equal to P naught plus rho g h. So this is only valid if and only if rho is constant. So let's just say, I'll just put is constant. So let me just go ahead and do the derivation for the methane portion, which is what we're going to be mostly doing for part A of the problem, and you can see why this assumption doesn't work in that case. So we're going to start off with this same differential form right here, and then we're just going to separate and integrate, but now we need to just be wary that the density is going to change with our elevation. So I'm going to say that this is equal to the molecular weight of the gas times the gas constant over the universal gas constant. Sorry, this is a gravitational constant. This is universal gas constant, and this is the temperature. Let's see, and I left off the pressure. So this is just from the ideal gas law, PV equal to nRT, and you can go ahead and derive that. But we're going to use this expression now, and we're just going to separate it and integrate, so we get the integral from PB to PA of dP over, now I'm dividing the pressure over, and I get over P is equal to, and then we have a negative here, sorry, and that'd be a negative molecular weight times gravitational constant over RT, and then we're going to integrate. So it's isothermal, so we can pull the T out front here, and then we're going to go from, I'm just going to call it ZB to ZA and DZ. Okay, now, so just kind of anticipating here, what I'm going to do is I'm actually going to invert this integrand here. So I'm going to say that that is equal to a negative integral from PB to PA dP over P, and that's just ditto. Okay, and then I'm going to have these negative signs cancel, which will be nice. And then this is going to give us a natural log, and the simplest form will be to write it as natural log of PB over PA. And then it's going to equal to, this is just going to be ZA minus ZB, this when we evaluate this, times this quantity right here. And that is just ZA minus ZB is equal to H. So I'm just going to do all that in my head right now. So I'm going to end up with an expression where PB is equal to PA times exponential of, and now the negatives cancel out, so it's positive now. So we have the molecular weight of methane times the gravitational constant over RT, and that's going to be multiplied by our height. So that is going to give us the pressure at the interface between the methane and the oil. And I'll go ahead and do the calculation now. 1 second. Okay, so we have the pressure we're given is we're given it in gauge. So let's just go ahead and do that. So it's 10,000 psi, and then we're going to add on 1 atmosphere of pressure. 1 atmosphere of pressure is 14.696 psi, and that's going to be multiplied by the exponential of, and now the molecular weight methane is 16 grams, so 16 kilograms per 1,000 mole, and then that's going to be multiplied by 9.81 meters per second squared, and then our height, which was 10,000 feet, converted to meters is 3048 meters. And then we're going to divide by the universal gas constant, which is 8.314 joules per mole Kelvin. 1 joule is kilogram, is it meter squared? Yeah, meter squared per second squared. No, it's kilogram meters. Hold on. 1 joule is a kilogram meter squared per second squared, and then so that's joule, and then we want mole Kelvin on the bottom, and then we're going to multiply by temperature in Kelvin, which we're given the temperature is 100 degrees Fahrenheit, so we need to convert that using the identity that temperature in Kelvin is going to equal to, let's see, 100 minus 32, so that's temperature in Fahrenheit minus 32, and then that quantity multiplied by 5 over 9, and then add 273.15. So that's going to give us 310.93 Kelvin. Okay. Yeah, then you just crunch the numbers. Should get, I did this earlier, and I got 1221 psia. So 1221 psia is what the pressure is at the interface between the methane and the oil. So the reason why we had to go to the ideal gas law is because the density was not constant. So that's important to keep in mind here. But in part B, it's a lot simpler because the fluid, the oil, is incompressible, which means that the density is constant, which means that if we go back up, which means that I can use this derivation right here because the density is constant. So we just know that the pressure at the point C is going to equal to pressure at point B plus rho GH. So let's go ahead and do that real quick and finish up the problem. So we're asked to find PC minus PB, and then we know that PC is equal to PB plus rho of the oil times gravitational constant multiplied by capital H. So in the problem statement we are given that the specific gravity of the oil, so Sg, is equal to 0.75, and then we're given the density of water in imperial units, but the density of water in metric, in SI units, is just 1,000 kilograms per meter cubed. So this is what we're going to use. Then we can convert back to imperial at the end. So we're interested in PC minus PB. So that is going to, so PC minus PB, that is equal to rho. So we're going to have 0.75 specific gravity. So definition of specific gravity is just is equal to the rho of whatever substance you're interested in over the rho of W, the rho of water. So I'm going to multiply this by, let's see, just multiplied by rho W here. So then it should be 1,000 kilograms per meter cubed. Okay, and then we're going to multiply by 9.81 meters per second squared. And we're going to multiply that again by the height, and I'm converting it into metric, and I get 609.6 meters. Okay, so this is going to give us the answer in pascals, and we're going to convert it back to PSI. And so to do that, we just need to multiply. So 1 atmosphere is 14.696 psi, and then 1 atmosphere is also 1.01325 times 10 to the 5 pascals. So that will give us units in psi. So you crank this calculation out, you should get approximately 650 psi. Okay, yeah. So that would be the answer to part B. So pretty easy. The only difference between the manometer problems is that we just had the variation of the density of the gas to take into account with this. So that will do it.